10.4 Lesson 1, Polar Coordinates and Polar Graphs. Our objectives for today are 1. You will understand the polar coordinate system. 2. You will understand the relationship between the polar coordinate system and the rectangular coordinate system. 3. You will be able to convert polar coordinates to rectangular coordinates and rectangular coordinates to polar coordinates. So let's begin with something that we've been working with for years, which is the Cartesian plane or the XY plane, also called the rectangular coordinate system. So we have an x-axis, we have the x-axis, we have the y-axis, and of course this is called the positive x-axis because that's where you have positive x values. This would be the negative x-axis. And the intersection of the two axes is called the origin. So now we're going to look at a new coordinate system. What is a coordinate system? It's a way of assigning an address to a particular location on the plane. Like, for example, you might live at a particular address. How would the mailman find you? Well, you have a street name and a house number. Like, for example, you might live on Ralph Street, okay? Maybe your address is 9224. So your address will be 9224 Ralph Street. So that tells somebody who wants to find you to first find Ralph Street and then to find 9224 on Ralph Street. So a coordinate system is a way of specifying the location of a point in a plane. And we do that by either having an x-axis and a y-axis and an origin, or we can do it in a different way, and that's what we're going to look at today, the polar coordinate system. And we're going to not just look at the polar coordinate system, but we will also see the relationship between the polar coordinate system and the rectangular coordinate system. So with Objective 2, you're going to take your polar coordinate system and superimpose it with the rectangular coordinate system to establish certain conversion relationships. And then we're going to use that to convert polar coordinates to rectangular coordinates and rectangular coordinates to polar coordinates. Here we have the polar coordinate system. Before I do anything else, I mentioned for Objective 2 that we want to establish a relationship between the polar coordinate system and the rectangular coordinate system. So we will begin by superimposing the two coordinate systems in the same plane. So if we had the rectangular coordinate system, this is where the x-axis would be. And this is where the y-axis would be. And this would be the origin. And over here we have the positive x-axis. So that's the rectangular coordinate system. Now we're going to superimpose the polar coordinate system with the rectangular coordinate system, and we begin with something called the pole. And then we're going to have something called the polar axis. And those two will start to define our polar coordinate system. With the rectangular coordinate system, you have coordinates that are x comma y. So for example, this particular point, as I've drawn it, you can see that there's a 2 here and there's a 2 here. So this point has coordinates 2 for x and 2 for y. So those are called rectangular coordinates. Rectangular coordinates. And we'd like to just add a little bit more to our vocabulary list. So today we're studying the polar coordinate system, but of course before we had the rectangular coordinate system. Today we'll be learning about polar coordinates, And of course, we've been using rectangular coordinates for years, XY coordinates. Today we're going to be discussing the idea of a directed distance with reference to the polar coordinate system, but in fact, this is something that you did with the rectangular coordinate system as well. With the polar coordinate system, we'll also have a directed angle and something called a radial line. So we have our rectangular coordinates 2, 2 for the point that is shown here, and we'll go ahead and call that point A. And suppose I have a point B, then let's say point B is over here, and it would have rectangular coordinates 2 for x, but negative 4 for y. Or if I have a point C, and maybe it's over here, it could be negative 3 for x and positive 4 for y. So even with rectangular coordinates, we have the idea of a directed distance. So remember, with the rectangular coordinates, the x-coordinate tells you the directed distance from the y-axis. So how far is point A from the y-axis? Point A is 2 units to the right of the y-axis. Where is point C in reference to the y-axis? It is 3 units to the left of the y-axis. Where is point C in reference to the x-axis? Point C is 4 units above the x-axis. Where is point B in reference to the x-axis? Point B is 4 units below the x-axis. And because it's below the x-axis, the y-coordinate of point B is negative. So the x-coordinates told you the directed distance of a point from the y-axis, whether it was to the right of the y-axis or to the left of the y-axis. And the y-coordinates told you the directed distance from the x-axis, positive y-coordinate if you have a point above the x-axis, and negative y-coordinate if you have a point below the x-axis. So we worked with the concept of directed distance even with rectangular coordinates. So now let's look at the relationship between the two coordinate systems. So you can see that I've drawn the x and the y axes in red, and here is the origin, and we have the positive x-axis here. And in this plane, we're going to superimpose a new coordinate system with the rectangular coordinate system that you see in red. So when we superimpose the polar coordinate system with the rectangular coordinate system, there is going to be something called the pole that will coincide with the origin of the rectangular coordinate system. And there's going to be something called the polar axis that will coincide with the positive x-axis of the rectangular coordinate system. So with the rectangular coordinate system, we had the x and the y axes, and we had an origin. With the polar coordinate system, the pole and the polar axis is going to be what defines the coordinates of points in the plane. Points in the plane will now be assigned polar coordinates with reference to the pole and the polar axis. So for example, suppose you have a point here. How do we assign polar coordinates to point A that I just showed in red? The polar coordinates for point A will be r theta. And what is r and what is theta? We should begin with theta. We will begin with theta. Theta is the directed angle from the polar axis. Why do we say directed angle? Just like with rectangular coordinates, we had directed distances from the y-axis and the x-axis. You could have a point that's to the right of the y-axis, in which case the x-coordinate would be positive, or you could have a point to the left of the y-axis in which the x-coordinate could be negative. So when we talk about theta in polar coordinates and we say the directed angle from the polar axis, what we mean is when you learned about trigonometry, and for example, when you learned about the unit circle, you learned about angles of rotation. You could have the initial side of the angle along the positive x-axis, or right now the polar axis, and if you rotate the initial side of the angle counterclockwise, you will have a positive angle measure, whereas if you rotate the initial side of the angle clockwise, you will have a negative angle measure. And that's why we say theta is the directed angle, because to get this particular terminal side, of the angle, there are different ways you can go from the initial side to the terminal side of the angle. One way is to rotate counterclockwise by an angle of rotation that is pi/6 radians. Another way is to rotate clockwise by an angle of rotation that is negative pi, negative 3 pi/2, and finally when you get here, negative 11 pi/6 radians. So what do we mean by the directed angle? We mean we could either rotate the initial side of our angle counterclockwise, in which we will get a positive angle of rotation, or we could rotate the initial side of our angle clockwise, in which we will get a negative angle of rotation. So in that way you have a directed angle from the polar axis. Furthermore, these are not the only two possibilities for the angle of rotation or the terminal side that I have sketched here. These are not the only two possibilities for the terminal side that I have sketched here, and I will highlight that with black. So that's the terminal side of our angle, but these are not the only two ways you can assign an angle of rotation to get that terminal side. There are many angles of rotation that are coterminal with the angle that I have sketched here. Coterminal angles are in standard position and they have the same terminal sides. So these two angles, theta is equal to pi/6 radians, as well as theta is equal to negative 11 pi/6 radians, are coterminal angles, and they are directed angles because one is rotated counterclockwise and the other is rotated clockwise. But in fact, there are an infinite number of angles of rotation that are coterminal with the angle that I have shown here in my diagram. And all you have to do is, for example, here I have an angle of rotation that's pi/6 radians. You can add to that a complete rotation counterclockwise and you will have a coterminal angle having the same terminal side. So in fact, any angle here that's written as pi/6 plus 2 pi n, where n is an integer, will give me a coterminal angle to the one that you see there in black. And the same here, I can write plus 2 pi n, where n is an integer, to get coterminal angles to the one that is sketched in our diagram. So I just wrote down additional vocabulary that we have been using in the last couple of minutes of the lesson. So now we understand what we mean by directed angle from the polar axis. So let's begin to assign a set of coordinates, polar coordinates for point A that I have highlighted here in green. So we can use not just one particular value for theta, but any number of values for theta. So pi over 6 is one possibility. You can also do negative 11 pi over 6, and so on. So in fact, you can have any other angle that's coterminal with pi over 6 or negative 11 pi over 6. So now both of these angles are coterminal. They give you the same terminal side, which is right here, which I'm sketching in black. And the next part that you have to do is assign a value for r. So what is r? R is the directed distance from the pole along the radial line, which is, of course, the terminal side of our angle of rotation. So our radial line is the terminal side of the angle of rotation. And what do we mean by the directed distance? You will see when I have an alternative way of assigning coordinates to point A. But for now, you're just going to look at how far point A is from the pole. Here's point A. Here's point A. And you can see here that this number is 4, signifying that point A is on a circle centered at the pole that has a radius of 4 units. And in fact, on this circle that I'm sketching now, any point that's on this circle will have an r value that's equal to 4. So this particular point, point A, is on the radial line that I'm sketching now, which has an angle of rotation of pi over 6 radians or negative 11 pi over 6 radians. And it is on that radial line, and it is 4 units from the pole. So we say point A has polar coordinates r theta, and we're going to write that point A has coordinates 4, comma, pi over 6, or alternatively, you could also write 4, comma, negative 11 pi over 6. And if I were trying to sell the polar coordinate system to you, I would say, but wait, that's not all. We can have even more ways of assigning coordinates for point A. So let's mark point A clearly. This is where point A is. Here's an alternative way of assigning a coordinate, a set of coordinates, a set of polar coordinates for point A. You can see that our angle of rotation that we used, the terminal side of the angle is here. This is the radial line. Theta is equal to pi over 6. Alternatively, you could use a radial line that's opposite the one that we have here. So we can use the radial line that is opposite the one that we have here. So we could use the radial line. Theta is equal to 7 pi over 6. So that would be our angle of rotation. Theta is equal to 7 pi over 6, or any of its coterminal angles. If you wanted to use a negative angle for that, you could write theta is equal to negative 5 pi over 6. If you use that for theta, then what would r have to be for the same point A? For the same point A, let's say we use theta is equal to 7 pi over 6, or you could also write negative 5 pi over 6. What would r have to be? Well, it's the same point A, but remember what r is. R is what we call the directed distance from the pole. So what do we mean by the directed distance? So if the terminal side of your angle is over here, as I'm about to sketch now in green, that's where the terminal side of the angle is. And if your point is on the terminal side of the angle, then you will express the distance your point is from the pole as a positive number, like we did before. Point A was on the terminal side of the angle of rotation pi over 6 radians, or negative 11 pi over 6 radians. And because point A was on the terminal side of that angle of rotation, we're going to say that point A is positive 4 units from the pole. However, when you use the angle of rotation 7 pi over 6 radians, or negative 5 pi over 6 radians, that would be this angle here. Let me go ahead and sketch it again for emphasis. So we're talking about this angle of rotation. That's the terminal side of the angle 7 pi over 6, or negative 5 pi over 6. Point A is not on the terminal side of this angle. It is in fact on the ray that is opposite this angle, this terminal side of the angle. And because point A is on the ray opposite the terminal side of the angle, we're going to say the distance from the pole, or more precisely, the directed distance from the pole, is going to be negative 4 units. So we write negative 4 units for both of these cases. So we have looked at the pole, the polar axis, the polar coordinate system. Polar coordinates are theta. And we've talked about what r and theta represent. R represents the directed distance of a point from the pole, and theta represents the directed angle of a radial line with respect to the polar axis. And one thing that you see right away is that there is not a unique representation for a point in polar coordinates. You can see, for example, that as I've done on the screen now, I've written the same point A with 4 sets of polar coordinates. So there is not a unique representation for a point in polar coordinates. You could have different polar coordinates representing the same point. That was not the case with the XY plane. That was not the case with the rectangular coordinate system. There was a unique set of coordinates to represent a point in the XY plane. So now you should understand the polar coordinate system, and now we will look at objective 2. You will understand the relationship between the polar coordinate system and the rectangular coordinate system. And once you understand that relationship, you will be able to convert polar coordinates to rectangular coordinates and rectangular coordinates to polar coordinates. So how do we understand the relationship between the rectangular coordinate system and the polar coordinate system? Let's superimpose the two coordinate systems. So here we have the x-axis, and here we have the y-axis. And you will observe that the pole from our polar coordinate system coincides with the origin from the xy plane, and of course the positive x-axis coincides with the polar axis. So to establish the relationship between the coordinates of a point, rectangular coordinates and polar coordinates, consider the following. Consider a point A with rectangular coordinates x, y. Make the observation that this point A is a point on a circle centered at the origin with radius r units. And in rectangular coordinates, the equation for a circle centered at the origin with radius r units is x squared plus y squared is equal to r squared. The radius of our circle that I sketched in green is r. And of course, if you look at the polar coordinate system, this circle has the same radius as we just discussed in the rectangular coordinate system, because the pole and the origin coincide, so any point on the green circle will be the same distance from the pole as it is from the origin in the rectangular coordinate system. So the R value is the same regardless of whether you're thinking about the rectangular coordinate system or the polar coordinate system. So right now, we already have an equation that relates the x and y coordinates of a point in the xy plane to the r coordinate of a point in the polar coordinate plane. Furthermore, we can use trigonometry as follows. So point A lies on the terminal side of an angle of rotation, where the initial side is, of course, the polar axis. And there is an angle of rotation associated with that, and we will label that theta. And point A is on a circle of radius r. So this distance here is r. You remember the unit circle definitions of the trig functions sine, cosine, and tangent. Using the unit circle, we define sine of an angle of rotation theta to be y, cosine to be x, and tangent to be y over x. And in fact, what we have here is something more general than the unit circle. The unit circle has a radius of 1, but now we have a circle whose radius is r. However, you can extend the definitions of the trig functions from the unit circle to a circle of radius r very easily. Sine of theta will just become y over r, cosine of theta will just become x over r, and tangent of theta will stay the same. And of course, you can even relate these definitions of these trig functions back to right triangle trigonometry, but we won't go into that now. But these are the definitions of the trig functions sine, cosine, and tangent. And we can use these to do the following. If you solve for x here, you get x is equal to r times cosine theta. And if you solve for y here, you get y is equal to r times sine theta. And we have tangent of theta is equal to y over x. So if you put these four together, these four equations establish the relationship between polar coordinates and rectangular coordinates. Now let's go ahead and take a look at objective 3. You will be able to convert polar coordinates to rectangular coordinates and rectangular coordinates to polar coordinates. So let's look at the first part of it. You'll be able to convert polar coordinates to rectangular coordinates. To do that, we're going to use these two relationships. So let's begin with a point whose polar coordinates are known. So suppose we have an angle of rotation that's pi over 6 radians. So this would be the terminal side of the angle. So we have the radial line pi over 6. And suppose we have a point on this radial line that is 4 units from the pole. And we'll call this point A. So the coordinates of this point in polar coordinates would be r theta. The angle of rotation is pi over 6 radians. So we have theta is pi over 6. And r would be 4. So what would be the rectangular coordinates of this point? And how can we find it very easily? Just use the relationships that we established to find the x and y coordinates of point A. So the x coordinate of point A is given by r times cosine theta, and the y coordinate of point A is given by r times sine of theta. So how can you get the x and the y coordinates? Just substitute what you have for r and what you have for theta into r cosine theta and r sine theta. So we will have 4 times cosine of pi over 6, comma, 4 times sine of pi over 6. So you have to remember some trigonometry here to be successful. So cosine of pi over 6 is going to be square root of 3 over 2. So you have 4 times square root of 3 over 2. And sine of pi over 6 is going to be, sine of pi over 6 is 1/2. So you have 4 times 1/2. So when you do that, you get A would be 2 square root of 3 comma 2. So those are the rectangular coordinates of the same point, A. So this point A has coordinates 2 square root of 3 comma 2. These are the rectangular coordinates of point A. And you can see that the y coordinate should be 2. You can see here 2. And if you use your calculator to find what 2 times square root of 3 is, you'll see that it's somewhat less than 4. So you just saw an example where we converted polar coordinates to rectangular coordinates, but you can also convert rectangular coordinates to polar coordinates. So theorem 10.10, coordinate conversion, is what we just established earlier. The polar coordinates r theta of a point are related to the rectangular coordinates x, y of the point as follows. And you will see, of course, like number 2 here, we had seen why that relationship is true earlier. And we also have tangent of theta is equal to y over x. We saw earlier why that's true. And we have x is equal to r times cosine theta. We saw earlier where that came from. And y is equal to r times sine theta. And we saw earlier why that's true. Consider point B, which I showed in red, with rectangular coordinates negative 1, 1. Negative 1 for x and positive 1 for y. And suppose we want to write the polar coordinates for point B. In the previous example, we went from polar to rectangular, and in doing so, we used the coordinate conversion equations listed under 1 here. In this example, to go from rectangular to polar, we will use the coordinate conversion equations listed here in 2. We need to begin by finding what we should have for theta. What is going to be the directed angle from the polar axis? So here's the polar axis, and what's going to be the directed angle from the polar axis? So you can use tangent of theta is equal to y over x. So you have tangent of theta is equal to y over x. Y is 1 and x is negative 1. So tangent of theta is equal to 1 over negative 1. Tangent of theta is equal to negative 1. Now if you solve for theta using the arctangent function, you'll have theta is equal to the inverse tangent or the arctangent of negative 1. And the angle that you get is actually going to be negative pi over 4 radians. So you will get this angle negative pi over 4 radians. And you'll notice that point B is not on the terminal side of the angle. It is actually on the ray that's opposite the terminal side of the angle. So if you are going to use this angle, your R value would have to be negative. However, you could just add pi to negative pi over 4, and that would give you 3 pi over 4, which would be the angle that you see that I sketched earlier in gold with dashed gold. That's the terminal side of the angle with an angle of rotation equal to 3 pi over 4 radians. So for the polar coordinates of B, I will choose 3 pi over 4 radians so that r can be a positive value. But that's optional. You could choose negative pi over 4 radians and r would be negative. So now I'm going to find out what r should be. And to figure out what r should be, I will use the second equation under number 2. So I have r squared is equal to x squared plus y squared. So I have negative 1 squared plus 1 squared. So r squared is equal to 1 plus 1. R squared is equal to 2. So r is equal to the square root of 2. And again, because I'm using the angle of rotation 3 pi over 4 radians, and point B is on the terminal side of the angle, the directed distance from the pole will be positive square root of 2. I could have also used the angle of rotation negative pi over 4 radians, and the terminal side of that angle is shown here in green. But point B is not on the terminal side of that angle. It is on the ray opposite the terminal side of that angle. So if I'd done that, I would have to choose r to be negative square root of 2, because remember, r is the directed distance from the pole. So we just saw one example in which we converted polar coordinates to rectangular coordinates, and we saw a second example in which we converted rectangular coordinates to polar coordinates. We will conclude our lesson by doing something very quickly with some points that are easy to work with in both rectangular and polar coordinates. Suppose we have point C with rectangular coordinates 0 for x and negative 4 for y. We can easily write the polar coordinates of point C just by visual observation. You can see that the angle of rotation from the polar axis would be 3 pi over 2 radians. So here's the terminal side of the angle, and you can see that point C is on the terminal side of the angle, and it is 4 units from the pole. So the rectangular, so the polar coordinates of point C, one set of polar coordinates for point C would be, the angle of rotation is 3 pi over 2 radians, and the directed distance from the pole for that angle would be 4 units. So we were able to go from rectangular to polar coordinates in this example just by visual examination. Suppose you have point D with polar coordinates r theta. The angle of rotation from the polar axis is pi over 2 radians. And here's the terminal side of the angle. And you can see that point D is on the terminal side of the angle, and it is 2 units away from the pole. So r is positive 2. The directed distance from the pole is 2 units. If you wanted to write the rectangular coordinates for point D, this is something that you can do visually just by observing that point D is on the y-axis, and it is 2 units above the x-axis. So the rectangular coordinates of point D would be 0 for x and 2 for y. And of course, for more complicated problems, you can use the coordinate conversion equations in number 1 here to go from polar to rectangular coordinates if you know r and theta. And you can use the polar coordinates here, the coordinate conversion equations here under number 2 to go from rectangular to polar. So we will assign some polar coordinates to certain points in the in the polar coordinate plane to conclude our lesson. So suppose we have this point here. Suppose we have another point maybe over here. Suppose we have a third point over here, and maybe a fourth point that would be right here. So we're going to name these 4 points A, B, C, and D. And what we'd like to do is we'd like to assign one set of polar coordinates for each point. Again, remember, polar coordinates are not unique representations, meaning I could have more than one set of polar coordinates that would tell me the location of each of my 4 points. So for point A, one easy way to assign polar coordinates would be to make the observation that this point A is on the radial line pi over 3. So I can choose theta to be pi over 3. And if I do that, then I can see that r, the directed distance from the pole, is 2. It is 2 units from the pole. For point B, I can see that point B is going to be on the radial line 5 pi over 6. The angle of rotation here is 5 pi over 6 radians. So when I write polar coordinates, theta would be 5 pi over 6, and r would be, this particular point is 6 units from the pole on the terminal side of the angle 5 pi over 6, so r would be 6. For C, the angle of rotation that I have is 4 pi over 3 radians. So here's the terminal side of the angle, 4 pi over 3 radians. And point C is 3 units away from the pole on the terminal side of the angle with angle of rotation 4 pi over 3 radians. So C would be 3 for R and 4 pi over 3 for theta. And D, it is on the terminal side of the angle with angle of rotation 5 pi over 3 radians. So you can write 5 pi over 3 for theta, and it is 4 units from the pole, so R would be 4. And of course, any one of these points, you can have other polar coordinates to represent the point. So let's work with C for that. So if you look at C, one other possible representation for the coordinates of point C in polar coordinates would be, consider the angle of rotation that is pi over 3 radians. So point C is on the ray opposite the terminal side of the angle. So if I choose my angle of rotation to be pi over 3 radians, then R would have to be negative 3 to represent the same point. Again, there are an infinite number of ways you can represent the location of point C using polar coordinates. Let's just look at maybe one more. And that is, let's say here you have the polar axis and you rotate clockwise, and the angle of rotation here would be 2 pi over 3, negative 2 pi over 3 radians, because we rotated clockwise, and because the terminal side of the angle would be over here where you see the green ray, and point C is on the terminal side of the angle, the directed distance from the pole would be positive 3. Today we worked on understanding the polar coordinate system. We also worked on understanding the relationship between the polar coordinate system and the rectangular coordinate system. And once we understood that relationship, we had some conversion formulas, and we were able to use those to convert between polar coordinates and rectangular coordinates.